Hello, everyone. In the last class, we just talked about the concept of thread. So you should know that thread is the basic unit for scheduling. And it means if there are multiple threads in one single process, uh, the thread will be the unit to get the CPU to execute some instructions, but not the process. Uh, if there are multiple threads in one process, it also means the process the process is still the basic unit to get the any kinds of resources such as the address space and the open files. But it's not the process will not be the unit to get the CPU. So the CPU will be allocated to a certain thread inside this process. But all the threads in the same process, they will share the same address space, but they have different states while they are executing different instructions. So different threads in the same process have the same address space, but they have different states, such as running and blocked and ready. Also, they have their own information relevant to the execution state, such as the pointer to record the instruction number, and the stack. They have their own execution information. So you just need to learn about the basic difference between the thread and the process. It's enough for this part, for this section, for section 2. We also learned something about inter-process communication. And as I said, in my opinion, it's the most important and it's most difficult part of this for this course. So I'm gonna slow down and explain the details as much as I can so that you can learn how to uh, handle these three typical IPC issues. So when we talk about inter-process in communication, it means there are multiple related processes and they need to communicate with each other. And the way to communicate with each other is to, there are three different ways. So the first one is to, sometimes multiple processes, they need to share a certain data or a certain file or share the data. So they have to make sure that only one process can get into the critical region to access the shared data or file at the same time. So this issue is called a mutual exclusion. So it means multiple related processes, they need to access some shared data or files in a mutual exclusion way. So this is the first way to communicate among multiple processes. Also, sometimes the processes, they need to cooperate to finish a certain job, such as when if for example, if we recall the case about the spooling directory to print some files on the shared printer, multiple processes, they can put their files into that directory, the special directory, and then the printer just get one after another out of that directory to put them into the printer to get print out. So in this way, the printer and the process which send a certain file to that directory, they need to finish this printing job in a cooperative way. So process A has to put the file into that directory first, and then the printer can get the file out of that directory and to print it out. So they have to, if the process didn't put any files into that directory, the printer has to wait. And if the directory is full of the files which are waiting for the printing, waiting for printing, it means the next process needs to print any file, it has to wait. So you can say in the second issue, we need to control the synchronization among multiple processes, so that sometimes if this process needs to wait for something to happen, usually we call this case as a synchronization case. And after we explain the meaning of synchronization, you can see the mutual exclusion. It can be viewed as a spatial synchronization, right? Because mutual exclusion needs to control multiple processes to get into their own critical regions, one after another. So if there is already one process which is already in its own critical region, the other processes need to get in the critical regions to access the shared data or files. They have to wait. But the event they are waiting for is very special. The event they are waiting for is they need to wait for the process getting out of its critical region. So basically, we can take the mutual exclusion, the first IPC issue, we can take it as a spatial kind of synchronization. So these are the first two issues we need to handle relevant to the IPC problem. And the last one is much simpler compared to the first two issues. It just need to use some calls or primitives to pass information from one to another. So I just, before we learn anything new in this class, we have to take how to say, we need to give you this detailed review about the content we just learned in the last class. Because if we cannot recall the content in the last class, or if we haven't grasped the basic concepts or the ideas relevant to the following parts, it's very difficult for us to understand the whole important content in this section. So I just give you the review about the three basic issues relevant to enterprises communication, and you can recall this. You can recall the explanation about this outline of this section, because we just explained that the first two parts is about the problem description. In these two parts, we just learned what we need to handle for the first issue. We need to make sure that multiple processes, they access the shared data or files in a mutual exclusive way. So also in the last class, we just introduced some simple proposals to handle the first issue in this part. But as I explained, it's those proposals, they sound available, but they actually they are not put into the real world because they have kinds of defects, and we usually don't adopt those proposals to handle this issue. In this class, we're gonna learn some more proposals about the first issue, and the important part for this class is about the semaphores. We just emphasized this part in the last class. You can see we'll learn how to solve the first issue, how to make the multiple process share the data in all the files in the mutually exclusive way based on the Peterson or some hardware instruction. Also, we're gonna learn more generalized proposal to handle this mutual exclusion issue. Also, semaphore can be used to handle the issue relevant to synchronization. So you can see semaphores, they just provide us a very useful method to handle both issues, to handle the first two issues. So it's very important for you to understand the basic principles and the basic mechanisms to use these semaphores to handle some classical IPC problem. Also in this class, we're gonna learn this part about the sleep and wake up. This proposal, this way, you can see it has it works sometimes, but in some cases it's very complicated to make it work again. So we just we're gonna take a quick look about the fourth part, and we're gonna get into the fifth part, semaphores. That's the plan for this class. So after we learn the problem to be solved relevant to the mutual exclusion, and we know that we can use Peterson or some instructions to solve it, but usually we'll suggest you to use semaphores to give a more generalized method to handle those issues, because this way this semaphores can provide more generalized solutions relevant to both synchronization and mutual exclusion. So this is a plan for this class. But before that, before we learn anything new, we have to review some important content which we discussed in the last class. So we have first we need to recall the concept about race conditions. If multiple processes, they need to read or write some shared data or files, and you can see in the same computer, the final results can differ from the different execution order. If the execution order of instructions changed, the final result might change too. So we have to avoid such race conditions. And how to avoid this kind of race conditions, we need to make sure that multiple processes get into their critical regions at different time. So first we need to recall this critical region, this concept. And also I need to explain this simple example to you again, but in a simpler words, okay? In some simpler words to explain it to you again. If you recall this example, you can see we suppose there are two processes. We use these two processes to order tickets for two different users, and the expected value for x should be x minus 2, because after two processes ordered one ticket separately, respectively, the x should be set as x minus 2, right? But we just show you in the same computer, while these two processes are executed in a parallel way, it's possible for them to execute the code in this way. First, these two instructions, and then these three instructions, and then this is the last instructions. We just separated into 6 different instructions. Actually, this is not an instruction, but we can we just assume this code will be compiled into one instruction to make this problem simpler. Okay, so if the execution order for these 6 instructions are like this, you can see the final value of x is set as x minus 1. So that's the problem, because it means that you just sold one ticket to two different users, because after two tickets are sold to two different after the tickets is sold to the two different users, the number of the tickets just gets one get decreasement by 1, right? Gets subtraction by 1. So it's a mirror, it's an error caused by the different execution order of instructions, and we need to avoid these risk conditions. So the basic way is to make sure the different processes, they get into their critical regions to access the shared data at the same time. So our goal is to achieve this mutual exclusion. We need to make sure the process A, while process A is in this critical region, because for process A, all the code relevant to the shared data x is called in the critical region, and the same to process B. So if process A is in this critical region, then process B is forbidden from getting into process B's critical region, which are these 3 similar instructions. So that's our basic goal. The problem is how to achieve this goal. And you can see we have, before we discuss any proposals to handle this issue, to achieve this mutual exclusion, to achieve this goal about mutual exclusion, we just list 4 conditions. Let's just recall this, take a quick look at these 4 conditions again, okay? So these 4 conditions must be satisfied if you want to handle this issue correctly. It means no 2 processes may be simultaneously inside their critical regions. Of course, this is our goal, right? Also, no assumptions may be made about speeds or the number of CPUs. It means you cannot assume that there is only one CPU, and you cannot consume the process in the critical region. It can finish its job. It can run all its instructions or relevant in the critical region very fast. You can't make any of these assumptions, because maybe if there are multiple CPUs, the other processes, they can they can share, they can access the shared data or files in another CPU if we don't control the whole procedure correctly. So we can't assume that about anything relevant to the CPU speed or the numbers. Also, the third condition is that we just we should know that no process running outside its critical region may block any process. So if you are not in the critical region, if you are not executing any instructions relevant to the shared data, you have no right to block any other processes. So this is the third condition. And the fourth one means no process should have to wait forever to enter its critical region. It means for each process needs to get into its own critical region, this process should be finally get into its critical region. You cannot let the process just wait forever. So we can check this figure to understand those four conditions in a more straightforward way. In this figure, you can see we suppose there are two processes, and the gray box, the gray rectangle box means the critical region for each one. So if process A is already executing some instructions relevant to the shared data or files, when process A is already in its own critical region, we can see in this figure at this point, it means maybe the CPU just scheduled process B to replace process A to use CPU. So at this point, if process B is using CPU instead of process A, process B wants to get into its process B's critical region. This operation will be this request will be denied because process A is already in the relevant critical region. So process B has to be blocked. The state of the process B will be switched from the running state to the blocked state until process A leaves its critical region. At this time, it might emit an interrupt to show CPU, to show the operating system that there is no one in the relevant critical region. So process B at this time, process B can be waken up, the state of process B will be switched from blocked to the ready, and after the next time process B gets CPU to run the next instructions, process B can get into its own critical region. Also, you can see during this time, if process A wants to get in its critical region again, it will be blocked too. So through this figure, you can see the first condition is satisfied. No multiple processes can get into their critical regions at the same time. For the second condition, we just don't assume there is only one CPU. So you can assume that process A is running its instructions in CPU 1, and process B can run its instructions in critical regions in another CPU, in CPU 2. You can't make such a assumption. Also, after the process A, when the process A is not in its critical region anymore, process A cannot block B anymore. So it means if process A is already out of its critical region, process A has no right to block process B anymore. So process B can be waked up and to and to compete for the CPU to execute some instructions in its own critical region. And for the fourth condition, we can't make the process wait for the write to get into its critical region forever. Finally, it has its own chance to get in its critical region. So when we analyze different proposals to handle this mutual exclusion issue, we need to make sure that all these four conditions are satisfied. So you can see for this for the first proposal, we just discussed this. We can disabling interrupt, but if there are more than one CPUs in the same computer, this proposal doesn't work anyway, right? So you can it cannot satisfy the second condition. So this is a failure. We can't use this proposal to handle the issue. And for the second proposal, the local variables, you can see if we choose this way, it cannot make sure that no more than one processes stay in their critical regions at the same time. It's also possible that two or more processes will get into their critical regions during the same time. So this proposal is not adopted either. And today we're gonna learn some more proposals relevant to this issue. And here is another proposal called strict alternation. So this strict alternation will just choose set a variable called turn, and this variable, it just represents the whose turn it is to enter the critical region. So we start the new content from this slide. Okay, you can see we just list two processes here. The left part is for P0. Okay, we suppose there are two processes, and the left part is P0, the right part is P1. And this turn, this variable turn, we just set the initial value as 0. We use this turn to represent as it's initially set as 0. So it means in the very beginning, it's P0's turn to get into P0's critical region, right? After P0 executes all the instructions in the critical region, when P0 gets out of its critical region, then P1 can take P1's turn. P1 can take its turn to get into the critical region of P1. And then P0, P1, they have to take turns to get into their critical regions. You can check the code list here. We just check the left part, okay? Because the right part is almost exactly the same with the left part. So it means before P0 wants to execute any instructions in critical region, before P0 get into P0's critical region, it has to run this code. It means it will check if it's P0's turn. If it's not P0's turn, if turn is not equal to 0, it means if it's not P0's turn to get into the corresponding critical region, then P0 has to repeatedly execute this code to check if now this turn is 0, oh, it's not. So I have to, as long as P0 stays in CPU to execute the instructions, it has to execute the same instructions about this checking to check if 10 is changed as 0. If 10 is already set as 0, then the next instructions would be the instruction from the critical region. Then P0 can get into critical region. But if the 10 is not 0, then P0 has to repeatedly check the 10 to check if the 10 is 0 now by repeatedly execute this code, this while code. So this way we call it busy waiting, because you can see if the 10 is not 0, then P0 has to run this same instructions for a lot of times, right? So it's just continuously test the value of 10 until the value of 10 finally changed into 0. And this is called busy waiting. It means if a process is waiting for something to happen, it's just running the it's just running the instructions relevant to check if the event is happening in the CPU. So it means the process needs to use the precious resource. It needs to use CPU to wait for something to happen. While this process is waiting for something to happen, it is still in CPU. It still needs to run some instructions to check the event if the event happens. This is called busy waiting, and this busy waiting usually should be avoided, because you can see this this instructions to check if any event happens. It's just meaningless, because we can simply use interruption to notify the processes. Hey, the event you are waiting for is now happened. You don't need to take the resource. You don't need to stay in CPU to wait for this event to happen. You just get out of CPU to let other processes to run some meaningless instructions in CPU, and if you are waiting for something, you just get out of CPU and set the state as blocked, and when the event you are waiting for really happens, it will just emit the interrupt and showing the system that the event is really happened, and you can change your state from the blocked to ready. You don't need to wait for them. How to say? You don't need to take this precious computing resource. You don't need to take CPU to wait for something to happen. You can get out of CPU and wait for that event to happen. That's so usually we just avoid busy waiting, because it's just it wastes a lot of CPU time on running meaningless instructions, just repeatedly execute the same instructions to check the state. So it's useless, it's meaningless. Usually we just avoid the busy waiting, but there is exceptions, unless there is a reasonable expectation that the wait will be very short. It means if you are if the process is pretty sure that the event it's waiting for will happen in a very short time, then it can just it can just adopt this busy waiting way. Otherwise, usually we just suggest those processes block themselves and get out of the CPU and let other processes to let other processes with more with more how to say, with more detailed concrete codes relevant to the calculation, allow that kind of processes to use the CPU instead. So this is about the concept busy waiting, because this is a very basic concept really, in operating systems. So we just explain it in more details. You have to understand this concept busy waiting, and you need to know when to adopt busy waiting. Usually we don't adopt this way, but if you are pretty sure you just need to wait for a very short time, you can just adopt it. Because if you if you just need to wait for a very short time and you don't adopt busy waiting, it means you have to switch among multiple processes in a very short time, and it just wastes the resources in another way. So this is something you need to learn about busy waiting. Okay, let's come back to this strict alternation, about the proposals to handle the handle the issue relevant to mutual exclusion. Okay, we just checked this part. For no matter it's P0 or P1, before it gets into its own critical region, it has to check if it's if it is its own turn. If it is its turn, then it can get into the critical region. If it is not, then it has to wait in a busy way to by repeatedly by repeatedly executing this relevant instruction. So after the process get out of the critical region, if they are not executing any instructions relevant to the shared data or files anymore, it needs to set the turn as the other value. If this is for P0, it needs to set turn as 1. For P1, it needs to set the turn as 0. So it means after P0 after P0 gets in its critical region, the next process which can get into critical region should be the other process, should be 1. After P1 gets into critical region, then the next process which can get into the critical region should be P0. They have to take turns to get into their own critical region, just one after another, P0, P1, P0, P1, and we can make this process, make this procedure to alternatively gets into to show how these two processes gets into their critical region alternatively. So we can suppose the execution order of these two processes is like this. We can suppose the execution order of all of these instructions. We just use some numbers, use 1, 2, 3, 4 to represent the different lines, different code for P0, and use 5, 6, 7, 8 to represent the instructions executed for P1. So as you can see, this P0 and P1, they are both in the same computer. So the execution order of these 8 instructions, they can be randomly decided by the CPU scheduler, right? Because you have no idea at this moment CPU will choose P0 or P1 to get into the CPU. You have no idea the operating system, the scheduler will choose which process to use CPU. And there are lots of possible execution orders for this 8. Actually, it's not 8, only 8 instructions, because you can see these 4 instructions for P0 will be repeatedly executed, and so does P1. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 is for P0, and 5, 6, 7, 8. 5, 6, 7, 8 is for P1. As long as P1 is in CPU, it will repeatedly execute these 4 instructions, and so does P1. So this is a possible execution order. And in this order, you can see this strict alternation proposal, it works because the 2 processes just strictly alternate in entering their critical regions. First, it must be P0 because we set the initial value of turn as 0. So in the beginning, it's P0's turn to get in P0's critical region. So we suppose that in the very beginning, CPU just select P0, and 1, 2 will be executed, right? So when the CPU executes the first line of this process for P0, it will check if turn is 0. Oh, of course, the initial value of turn is set as 0, remember? So while if turn is not 0, then the CPU has to repeatedly check if their turn is 0. But now turn is already 0, so it just execute once for this line and move on to the next line. And in the second line, we just use this so-called pseudocode to represent some maybe it's a long segment of code relevant to the access to the shared data or file. So it means when we focus on this point, when while P0 executes some instructions in critical region, at this point, CPU might be allocated to P1, right? Operating system can decide at this point, P1 should replace P0 to use CPU. So after this point, P1 can execute some instructions from the first instruction in this process from line 5. Number 5 will just check the value of turn, right? And it check when it checks the turn, the value of turn, it will it finds that the value is 0. It's not 1. So it means at this time it's P0's turn to get in the critical region. It's not P1's turn to get in critical region. So P1, as long as P1 stays in CPU, P1 just completely executes line 5 until operating system, the scheduler or from operating system decide to let P0 take place of P1, replace P1 to use CPU again until the CPU is allocated to P1, then the P1 just get out of the CPU and let P0 use the CPU to run some instructions. And you can see the next time when when P1 gets back into CPU, according to the pointer, you can see P1 will just continue to execute line 5, right? So let's move on to this point. We suppose at this point, finally, the CPU will be reallocated to P0 again. Then P0 will execute some, will finish all the instructions in critical region and move on to the next line. In the third line, the turn will be set as 1. So at this point, you can see the system just knows that it's all the processes, they just know now it's P1's turn to get into the critical region. And then we suppose P0 keep running after it's while the P0 is executing a certain instruction from non-critical region. This line 4 can represent a long segment of code. Anyway, it's not any code about relevant to the shared data or file, so we call it non-critical region. So we suppose while P0 finish a certain instruction from non-critical region, the CPU is reallocated again. The CPU is allocated from to P1. Yes, to P1. At this time, CPU is not for P0, it's for P1. So when P1 gets CPU, it needs to execute the same line, right? Last time when it when it gets out of CPU, it's executing this line. And now it gets CPU back. It will continue to execute this loop. And at this time, it just finds that turn is already set as 1. So finally, at this time, P1 can move on to the next line because turn is not 0 anymore. At this time, turn is set as 1. It's already 1. As long as the value of turn is 1, it means it's P1's turn to get into its critical region. So P1 can execute all the instructions in the critical region, and we just suppose here while it's just get interrupt again, P1 will move CPU to P0, and P0 will continue to execute some instructions from line 4, and then when P0 move on to the next line to check if turn is 0, because P0 needs to get into its critical region again. At this time, you should remember the turn is set as 1, right? The turn is set as 1 here, and it's not changed as 0 yet, because line 7 is not executed yet. So at this time, when P0 runs when it's P0, when P0 runs instructions in CPU, it has to waiting for the turn yes, it has to waiting for the turn to be set as 0. So as long as P0 is in CPU, now it's P0's turn to it's P0's turn to just keep this busy waiting way to wait for the value of turn. And then we can see as long as P0 is in CPU, it's just continue executing the line 1 until the CPU is allocated to P1. So at this time, we can follow the sequence of the different instruction order. If we follow it, we can see now we are here. It means P1 instead of P0. It's P1 stays in CPU, and you can see according to this in execution code, P1 will finish all the job and execute line 7. So at this time, the turn is set as 0 again, and then P1 can move on to the next line to execute some instructions from non-critical region, and then 5, and then 1, and then 2. So in this execution order, you can see P0 here. P0 is in critical region. I just represent the critical region in yellow color. So you can see P0 is in critical region, and then P1 is in critical region here, because 2, 6 means the critical region, right? Line 2 and line 6. 2, 6, and 2 and 6, if they just alternate, they take this alternative turns to get in the critical regions, then everything is fine. These mechanisms can work well. But if we just change the execution order slightly, if we change the execution order of these 8 lines like this, you can see the problem just emerges. First, we suppose 1, 2, 3, 4. It means here the CPU switch from the CPU is allocated to P1, right? At this point, before this point, P0 is in CPU. After this point, P1 is in CPU. And I just ignore the, I think I don't need to analyze the detail about how they get into the critical region and how they get out of the critical region to execute the first 7 or 8 lines, right? We just here we just focus here, because at this time you can see this 1, 2, 3, 4, 1, they are all from P0. It means at this time, at this point, I just draw a vertical line here. The first vertical line means the CPU is the process in CPU is changed from P0 to P1. The second vertical line means that the process in CPU changes from P1 back to P0. And before P1 leaves CPU, you can see P1 is executing, just finish the execution of line 7. Before P1 leaves CPU, turn is already set as 0, right? And then P1, P0, and then here P0 gets CPU, and it can, because turn is already set as 0, so it means it's P0's turn to get into its critical region. So the first round, P0 can execute 1, 2, 3, 4 lines without any problems. And after this, when P0 wants to execute line 1 and get into the line 2 critical region, you can see the problem just happens. Because here, the turn is not 0. Because in line 3, the turn is set as 1. Because P0 just get out of the critical region from line 2. So it means the next process which can get into the critical region should be P1. You have to, P0 and P1, they have to take turns to get into their critical regions. But we can't control the execution speed. We can control when the CPU will be allocated to P0 or allocated to P1. After P0 finish all the 4 lines of code, the important point is here. After P0 just finish the first round of job, the P0 is still in CPU. The scheduler doesn't choose P1 to use CPU to run some instructions. So at this time, you can see if P0 still stays in CPU and runs the code for the next round, it will see that turn is already set as 1 because it's not P0's turn, it's P1's turn. So P0, as long as P0 is in CPU, it has to repeatedly execute line 1 to wait the line 7, to wait the execution of line 7 from P1, while P1, just before P1 leaves the CPU, P1 just execute line 7 and set turn as 0. The next time, you can see here, I just draw the third vertical line here. This next time when the next time P1 gets CPU back, it needs to continue executing its instructions from line 8, but not execute line 7 for the second time, because it's just finished the execution of line 7. So when P1 gets CPU back, while P0 is repeatedly executing its line 1, you can see here the P1 can finish its non-critical region, can finish line 8 and move on to the second round of P1 to get into the critical region, while P1 8 when okay, so next line should be line 5, right? And you can see the turn it will check if the turn is 1, and we can move back to here. The turn is 1, right? And then it can just, how to say, here line 5 is executed and the turn is set as 1, so P1 can get into critical region, and execute if P here P1 turn here turn is set as the value of turn is 1, right? Yes, it's 1. It's 1 so that means T1 can really get into critical region. It doesn't need to wait. But if the CPU is reallocated to P0, it has to execute some the line 1 for P0 and then back to P1, and it just execute this some instructions from critical region of P1, and then when the after it gets out of P1, then here, but here you can see the condition is already not satisfied. If you recall the four conditions about the mutual exclusion, we just in the third condition we can see we need to make sure that no process running outside its critical region may block any process. But if you watch this part marked with red yellow with red color, you can see while P0 is waiting for the turn to change back to 0, the other process, the P1, it's not in P1's critical region, because here I just need to circle it with another color. I just circled this part. While P0 is executing this line 1, circled by the green square, green rectangle, the P1 is not in its critical region. P1 is right here. Just finish its execution of line 7, and next time when it gets CPU back, it will continue to execute line 8. So it means the P1 at this moment, it's not in the critical region. It's not in the critical region, but P0 is blocked by P1. But P0 is blocked. If there is no critical, if there is no process which is already in its critical region, then the next process wants to get in the critical region should be satisfied, right? But you can see, you can check here, while P0 is waiting for something to happen, while P0 cannot get into its critical region. During this period, no process is in their critical region, right? P0 is not in its critical region, and P1 is not in its critical region either, because P1 is already get out of the critical region and set the turn as 0. So this is a problem, because if we just analyze the execution order, analyze the sequence of the execution of this second possibility, we can see it's just it seems work, right? It seems available that P0 P1, P1, P0, P1, P0, P1. It seems like they can just alternatively get into their critical regions without any problems. But if you watch this period, I just circle them with the green box a lot of times. If we watch this period, you can see during this period, the third condition is not satisfied. So we don't take this proposal as an available successful solution either. But here is a successful solution for mutual exclusion, Peterson's solution, because we just waste a lot of time on the explaining of that the last proposal, so we don't have time to explain about this Peterson solution in class. I have to suggest you to read through the code after the class. And you should notice that these two lines, about these two lines, you can check your textbook. It's different from the content on the slide. And the content in your textbook is wrong about, I mean, you just check these two lines. You should change the content like as the content on the slide, okay? Because when the basically the Peterson solutions idea is very simple. It's just need every process to call this function before before this process get into its critical region. Every process needs to call this enter region before it really gets into its critical region. And while the process is calling this function, if the process is not allowed to get into its critical region, this process will just repeatedly execute this line until the condition is not satisfied anymore. You can check the condition. This condition means if we suppose this is the code for P0, okay? Because we just suppose there are only two processes, P1 and P0 and P1. If P0 needs to get into its critical region, it just call this function and put 0 as in put 0 here as the parameter. So processes here it's 0 because it's P0 is calling enter region, and for P0 the turn is set as 1 but not 0. In the textbook, this is not other. This part is printed as processes. It's wrong. The turn should be set as 1. So when P0 when P0 executes this line, it will check if turn is 1 and if interested 1 is true. It means you can see here we just turn means whose turn. It's whose turn is it to get into the critical region, and interested this variable is used to represent if P0 wants to get into critical region. If it's 1, if interested is true, then it means interested 1 is true, it means P1 wants to get into. If interested 0 is true, it means P0 wants to get into critical region 2. So who can really get into their critical regions? Only the process matches to the matching to the turn can really get into its critical region. And when P0 wants to get into its critical region, it needs to call this, right? So P0 will check if it's P1's turn, and if P1 wants to get into the P1's critical region. If it's true, it means this line just show P0. No, you cannot get into your critical region because now it's P1's turn. You should change this part as this. It's P1's turn, and also P1 wants to get into its critical region. So as P1 wants to get into P1's critical region, and it's P1's turn to do so. So P0 needs to check this condition repeatedly until it's not P1's 0 or until it's the P1 is not interested into entering the critical region. So you can see if each process just call this function right before they get into the critical region, it will this two the values of these two variables will just coordinate the two processes get into their own critical regions in the correct way. And after they get out of the critical region, it needs to each process needs to call leaf region to set the interested as false to show the other process that I just get out of the critical region. Now I'm not interested in entering the critical region. I don't want to get into critical region at this moment. So after the process get out of the critical region, it will just call this function, and then you can see the other if there is another process waiting to its critical region by repeatedly executing this line, it can finally find that this condition is not satisfied any longer because the interested other is not true anymore, because that process just get out of its critical region and sets that value. So now get to its critical region. In this way, the two, because that process just get out of its critical region and sets that value. So now get to its critical region. In this way, the two processes, they can get into the critical region while all the four conditions are satisfied. So this Peterson solution is a success solution for you to understand. And if you can follow this execution order of this of P0 and P1, because we just suppose there are two processes, they have some data to share, they need to access to some shared data or files. We suppose there are only two processes, and if you follow this execution order, you can see they can get into their critical regions respectively. Also, there is no limitation about the order to get into the critical region. In the last solution, you can see they have to P0 and P1, they have to take turns 1 0 0 1 0 1 0 1. They have to follow this order to get into their critical regions. But in with Peterson's solution, they don't have to follow any determined determinate order. You can see here we just marked the critical region in the yellow color. First the P0 is in critical region, then P1, then P1, P1, and then P0. There is no fixed order for them to get into their critical region. And the way to understand how the Peterson's solution work is to just list all the values of these two key variables. So if you want to really understand how Peterson's solution work, you need to, for example, you need to list this value on the paper. For example, P after first three lines of P0 are executed, you can say in P0 other